I'm Jeremy Cooperstock, the director of the Shared Reality Lab at McGill University in Montreal, Canada, and I'm delighted to speak to you today about taking haptics out of the lab and into the wild as part of the IROS tutorial on haptics. Before I begin, I'd like to give credit to three outstanding members of our team who helped put much of this content together. Antoine Well-Duflos and Young Jae Yu are both postdoctoral fellows in my lab, and Jeffrey Blum is a PhD candidate with us. I should also mention that much of the content from the presentation today is out of our paper that we published in the Transactions on Haptics, entitled Getting Your Hands Dirty Outside the Lab. For those interested in this subject, wishing to dig a little bit deeper, I encourage you to consult our paper. Let's set the stage. In the real world, haptics are often delivered to us by devices in which we are in almost constant contact. Those may be our smartphones in our pockets or in our hands, or smartwatches worn around our wrists, or increasingly, different forms of wearables that are coupled directly to our bodies. I'd like to address some of the issues that arise when using these devices in real-world settings. So first, how do we use haptics in XR? XR being augmented, virtual, any kind of change of the environment through computer mediation. So there are three different classes I'd like to consider. The first is one of alerts. This could be, for example, a vibrational alarm telling you it's time to wake up. A second category could be delivery of semantic information, such as a numeric value telling you that you've just completed 3 laps around the track. Or a vibrotactile tacton, that's a vibrational icon that indicates some important information. For example, you're approaching your bus stop and it's soon going to be time to get off. And a third category of information is that of experiential haptics, where you're provided a richer sense of synthetic objects or a virtual environment. The example in the bottom right is taken from our cave environment at McGill, where we use haptics to synthesize the experience of walking on different ground surfaces, such as snow or ice or sand or pebbles. Most of you are likely already familiar with the controlled conditions of laboratory experiments. You've probably already run a number of these yourselves. In such environments, you might have wires everywhere, running under the floor, through the shirts of your participants, down their arms to their wrists, around the back of their necks, wherever it may be. You likely also use sophisticated hardware setups with lots of electronics and computers, and some of those pieces of equipment might be failure prone. Fortunately, in lab experiments, you typically have the experimenter right there, often right beside the participant, who can help troubleshoot if there are any problems. Now, such experiments and those conditions are certainly useful, but I'm going to make the point here that it is critically important when you're dealing with haptics to distinguish between what we can learn in those laboratory conditions as opposed to what we can learn from an in-the-wild study, where you don't have the same tools at your disposal and the preferences of your users or your participants are going to be somewhat different. So first, let's define what is an in-the-wild study. Well, Chamberlain provides a definition here as being research that involves the testing of prototypes in public spaces to see how they are adopted and used in everyday life. The rationale here is made very clear by my colleague Karen McLean in an article she published in 2009 titled Putting Haptics into the Ambience. There she makes the point that haptics are particularly well suited to background delivery, but this can also make them more susceptible to real-world confounds that we'll soon be discussing. And those real-world confounds are really the critical difference between what you have in a lab setting and what you find in the wild. Let's look at a few of those now. The first being attention and distraction. As you might expect, participants in a laboratory experiment are focused on their task. They're working in a controlled environment where you can avoid distractions, or if you want to provide a distraction, you have control over when it is delivered. In contrast, in the wild, It's uncontrolled. You have a noisy environment where interruptions and distractions of your participants can arise at any time. So participants will not be focused to the same degree that they are in that isolated time and space of a lab setting. And as a result, what you learn in the lab may not transfer all that well to the real world. A second characteristic of difference is that of the workspace environment itself. As I mentioned before, you may in your lab have wires running everywhere. And when you're using wired communication, it's much easier to keep all of your equipment in tight synchronization. In the wild, you need something that people can actually wear. And generally, that means it must be wireless. And when you go wireless, this introduces challenges to latency, the time delay between different events and the signaling and the actuation. And it also introduces challenges of synchronization, making sure that multiple events take place exactly when you want them. And that's especially a problem when you're dealing with multiple actuator setups. Now, fortunately, there are ways to overcome this, depending on the trade-offs you want to incur in terms of cost and latency and synchronization, but they are factors to consider. Here's an example of some equipment that we used in a controlled laboratory environment study. This was where we were looking at actuated variable friction shoes so that we could induce slips on demand, as if a participant were walking along and suddenly encountered a patch of black ice. The prototypes we built, basically housed in these disco-like shoes, were perhaps suitable for a laboratory environment without obstacles around and a very flat, smooth floor surface. But out in the wild, I very much doubt that this equipment would be usable or would even survive for a few minutes. It's completely impractical for the out of the lab, in the wild setting. So now let's turn to questions about hardware. And this section is really all about how you choose your actuators. What are you going to use for generating those haptic stimuli? And in this talk, I'm focusing primarily, exclusively in fact, on vibrotactile actuators. There are a number of different classes of hardware that have been discussed in other sessions here, but I'm going to be dealing solely with the most common types we encounter in consumer electronics devices, such as smartphones and smartwatches, that are vibrational in nature. So the researcher for such experiments, whether they're in lab or in the wild, has a choice to make. They can go with commercial, pre-existing systems, for example, haptics built into wristbands or gaming vests, shoe soles, and data gloves, or you can take the DIY approach and build it yourself, embedding haptic actuators into shirts, sleeves, gloves, bands, rings, and so on. In either case, there are so many actuators from which you have to choose. Each has individual performance characteristics. There are different levels of wiring complexity, in particular on the right-hand side of this page. There are definitely questions of fidelity, the robustness of the actuators. These are all factors to consider, and you have choices to make. So we'll talk about a few of these issues now. First, there's one of performance. Just like in audio, you have to keep in mind that higher quality hardware is not only more expensive, but it's also more expressive. At the low end of the spectrum, you have the low-cost coin cell style eccentric rotating masses, ERMs. These tend to have a slow response. It takes time for the motor to spin up before the vibration signal is imparted to the user. The problem with ERMs is more than just the slow response, though. It's that the frequency of vibration and the amplitude, the strength of that vibration signal perceived by the user, vary together. You can't separate the two. And they typically operate most efficiently at a single optimal frequency-amplitude combination. The next class, linear resonance actuators, or LRAs, have controllable amplitude, but they have a fairly fixed frequency band. They have a very high spike or steep rise up to that peak performance at which they resonate, and outside of about 10 or so hertz on either side of that peak, the amplitude falls off rapidly, and you just don't perceive the vibration anymore. The next class of actuators are piezos. These provide independent control of the amplitude and the frequency. They also boast a much faster response, usually around 3 or fewer milliseconds. So very useful if you want to make sure that you have very good timing sensitivity. They also offer a much wider frequency range than the previous classes of actuators, and physically they can be packaged in very thin form factors. But there's a drawback that makes them fragile. Another factor is they require a high voltage amplifier in order to achieve the power delivery requirements. Finally, we have voice coils. These are analogous to loudspeakers that we're used to in the auditory domain, and they also exhibit a very fast response, typically less than 5 to 10 milliseconds. A wide frequency range with a peak that can be controlled, depending on their manufacturing, anywhere between about 50 and 500 hertz. Now, let's take a look at how these actuators operate. These are two different instances of linear actuators, and visibly, they seem to be built in a very different manner. The shape of them, the way they move, but notice that they're both operating in a linear manner. The movement is along a single axis. One of them moves a sort of pin-like mechanism that vibrates against the encasing, and the second one, the electronica in the middle, uses a membrane that is vibrated by virtue of a magnet that moves up and down and contacts that membrane, imparting vibration to the user. When we're looking at such devices, it's also useful to consider the trade-offs between the amplitude of response that can be achieved with a certain mass and the flatness of the response that you obtain at different frequencies, all determined by what's known as the quality factor or the Q factor. You can see here a graph showing 3 different plots with Q values. The lower the Q value, the smoother or the flatter response across the frequency bands. But in turn, that means a lower peak amplitude. So if you're trying to deliver a strongly perceived vibration to the user or the participant in your experiment, you might need to sacrifice that smooth response and have a sharper or a higher peak in order to make sure that at that key frequency, you're able to impart that power of vibration. Speaking of power, energy is a factor we have to keep in mind because batteries wear down and deplete their charge. And this is really a critical factor when we're talking about in the wild experiments in particular, because tiny devices such as smartwatches that are often used in haptics experiments have correspondingly small batteries, and that means a small amount of energy reserves. If you're running your vibrational actuator significantly throughout the day, that's going to wear down the battery faster, and the participants may need to recharge that battery several times. And that means potential reduced compliance. Many people will be reluctant to have to take off their watch sporadically and recharge it rather than, let's say, once a day. It's one more headache to deal with. And that brings us back to the choice between commercial versus DIY systems. If you build it yourself, you could potentially put in a larger battery reserve such that you reduce the need for frequent charging. But that comes with a trade-off of the packaging and the stability or robustness of your system. In terms of the realities of power, Pebble, a smartwatch manufacturer who used to make a system that we used in many of our experiments, was quite clear in their documentation, cautioning developers to use the vibration feature sparingly because sustained use will rapidly deplete the battery. More modern devices, such as the Apple smartwatch, provide similar documentation for their developers, cautioning use of the haptic engine also consumes power, and using the engine too much may create a noticeable drain on the Apple Watch battery. This is not just with Apple, it's true as well for Android. In their power save mode, haptic feedback is automatically disabled, and that suggests that the drain on the battery from activating the actuator is non-trivial. Wearable devices, of course, are only becoming smaller, and that means the components are being pushed to become more and more power efficient, so that battery can shrink further while delivering, ideally, at least a full day of normal use. Another factor that is associated with typical users is wear and tear and damage. So devices, as you see here, will have different levels of durability. Perhaps the image on the left is more the fault of the user, but regardless, actuators over time will break down. And as they do so, they may exhibit changes in their behavior. So what you see here is a graph of an ERM with a constant amperage, constant current being supplied. That's the blue plot along the top. But you see that the amplitude response, as indicated by the red line, changes over time. And in particular, over that first 500 hours of testing, the very early part on the left of the graph, you have a significant fall off in the amplitude response. This is something to keep in mind, in particular when you care about ensuring consistent delivery of the strength of that vibration signal to your users. You might need to calibrate for that. You might need to be able to measure the perceived strength of the vibration and adjust accordingly. So remember, we want to generate vibrotactile effects, but not the sound. For your experiments, it's often critically important to know whether your participants are responding because they perceive the vibration, the haptic part, or whether they are responding because they perceive the acoustic elements, that they heard it rather than felt it. So for the actuator builders, this requires careful mechanical design. They need to work on damping the audio spectrum while retaining as much as possible of the haptic aspects. For the haptician, one suggestion is focus on lower frequencies in your interaction design. I'll turn to that in a moment, but that's where the haptics signals are perceived as opposed to heard. So to illustrate the problem, I'm going to play for you a recording that we took from one of our actuators in a Pebble watch. And if you're listening at home on speakers or headphones, beware, this might not be pleasant. I warned you. Now, that sound is from a microphone close up to the actuator, but you can imagine for a user in a fairly quiet environment, that's going to be awfully intrusive and disturbing, especially if it keeps recurring throughout the day. So what's going on here is that the actuator response in terms of its acoustic elements provide sound, they provide noise across the spectrum. And some actuators fare much better than others. The recording I played for you from the green plot is one that exhibits that acoustic noise across the entire spectrum. And it's particularly noticeable in the upper end where the audio really tends to dominate. Improved actuators, such as those from the baselet or the smartphone, have a nice fall off at the higher frequencies, making them less disturbing. So looking at that issue in a little bit more detail, we can look at the sensitivity of humans to the haptic perception, where the frequencies that dominate tend to be those around 250 hertz, at least for displacement, whereas the acoustic end of the spectrum tends to pick up with frequencies above 300 to 400 hertz. That's where you start hearing the vibration more than you're feeling it against your skin. Again, for the interaction designer, when you can stay to the lower end of those frequency ranges, you have a much greater chance of having your perceptions focused on the vibration that is perceived through haptics as opposed to through the ears. We want our vibrations to be felt and not heard. Next, let's turn to the questions of wiring and the communication scheme that your paradigm will use. When you're using multiple actuators in particular, the timing issues of getting your signal to your devices is critically important. You may also have synchronization challenges to deal with in terms of making sure that multiple actuators are going at the same time, or that the vibration is being rendered synchronously with some visual or auditory stimulus that you want to present. When you're doing this using wires in a lab setting, it's generally quite easy. You have full control of delivering the signal from your computer through the controller to the actuator, and you can give that signal at exactly the time that you want. When you take your system out into the wild, you generally have no choice but to go wireless. So the ideal in that scenario is where your computing device, perhaps your smartphone or some other portable unit, transmits the pattern to a controller that is also worn and wired directly to your actuator. That gives you better real-time control of the playout of that pattern. The third option is where the wireless system or the computer that is generating the pattern drives the playout entirely. The controller is with the computer and transmits the signal packet by packet with every little piece of that pattern coming in separate chunks of communication. And that entails a greater risk of jitter or of data loss as the packets travel with uncertain delivery and arrival times. So more challenges if you have to go that route. And finally, when you're talking about distributed systems, possibly with actuators over different parts of the body where you can't have a single controller wired to them all, or to different people or different places, you'll likely need to have different computing devices that are generating those patterns and sending them. And in turn, that means the need to synchronize clocks, especially when you want those patterns to be received and delivered at the same time. Now, we've talked a lot about the hardware choices that we have. What are the devices we're going to use? How do we wire them up? What are the power draw issues? How do we deal with the robustness and the propensity to damage that these devices may incur? But we're not done at that point because we still need to consider some other factors once we've settled on the choice of hardware. Well, let's turn to those now. First, we have to consider the coupling of the actuator to the body. If you have your device too loose, then the haptic signal might not be perceived by the user. The smartwatch here or the actuator in it may be vibrating, but if it's not pressed against the skin, the user might be oblivious to that signal. Conversely, if you make that strap too tight against the skin, not only will it be uncomfortable, but the haptic signal could be attenuated. In the worst case, the vibration actuator might not even be able to vibrate correctly because of those strong forces. So what you're after, much like Goldilocks and the Three Bears, is something that's neither too loose nor too tight, but just right, in the middle. Now, how do we get there? That's a challenge. I should mention as well that the quality of coupling, getting that not too loose, not too tight, is also important for sensors that might be embedded in your hardware. In a study that we ran last year, looking at the contact force estimation from raw PPG signals, we showed how the PPG signal, or the light emitted from that sensor, gets scattered and doesn't bounce back properly if the device isn't coupled firmly against the skin. So we need to achieve a reference tightness level that is as tight as you can get it without being too tight. And you want to be able to have that controllable and consistent both across an individual participant who may put their device on and take it off repeatedly throughout the experiment, or across multiple participants when you're trying to gather experimental data. And this is, of course, a key issue and challenge when you're dealing with experiments in the wild, where you don't have the experimenter handy to verify what the participants are doing with their devices. Next, we turn to the questions of habituation and adaptation. Habituation is where the user eventually gets used to the signal and no longer finds it distracting or bothersome to them. It sort of recedes into the background where they're aware of it, but it doesn't grab their attention and cause them to go, "What was that?" each time they perceive it. Adaptation is a property of the mechanoreceptors in the skin in which when you provide them a constantly repeated stimulus, eventually they start to degrade their response to it and stop paying attention. They no longer tell the brain this is important because it's just part of the background noise. So useless vibration, something that keeps going on as noise, is likely going to be ignored, whether it's through adaptation or through habituation. The signal must have meaning for the user in order for it to be relevant to them and for their brains to say, "What is that? Let me make sense of it." But a repeated pattern can nevertheless be annoying. So habituation may be useful in the case of ambient haptics, where you want users to be aware of something, but not necessarily consciously in the foreground. But adaptation, giving them that signal too often without enough rest, could be a problem in haptic delivery. Either case, you might mask or hide the effect of the signal. Let's look at those questions in the context of a pseudo-ambient vibrotactile display in the study by Jeff Blum.
Hi, I'm Jeff Blum, a PhD candidate at McGill University. If you wore a vibration motor and felt 2 vibration pulses every 20 seconds all day long, would it drive you crazy or would you get used to it? By get used to, I mean habituate to. Habituation is critical for building ambient awareness apps. Our goal was to see if people can habituate to frequent information-carrying vibrotactile tactons. If so, the vibrations should become a background awareness, with users able to ignore the vibrations when they are not informative, yet still become aware of salient changes, and also orient their attention to fully perceive the tactons whenever desired. Despite habituation's critical role, we found very few in the wild haptic habituation studies. We built an application called Mimic, described in the paper. A smartwatch strapped to each participant's lower leg rendered 2 vibration pulses every 20 seconds all day long. The vibrations' durations were linked to their partner's current activity. Even if their partner was completely still, there were always 2 small baseline vibrations conveying that Mimic was working. This feels like The first of the 2 vibration pulses gets longer the more their partner's leg is moving around, as measured by the accelerometer. And the second vibe gets longer when their partner's speed increases, as measured by GPS. So it would become very long, for example, when riding on a train. Walking, as pictured here, would add duration primarily to the first vibe, since the leg is moving up and down, but overall speed is low. It might feel like 8 couples wore Mimic for 3 weeks. All were in relationships and cohabitating, but apart at least 35 hours per week. Each day, they provided 5-point Likert scale responses ranging from strongly disagree to strongly agree as to whether Mimic was annoying and distracting. These are daily response percentages to Mimic being annoying, with disagreement on the left in blue showing habituation, and agreement on the right in red indicating difficulty habituating. Day 1 is at the top. Moving down through the first week of use, some participants had no trouble habituating from the start, while others struggled. If habituation takes place, we would expect less and less agreement that Mimic was annoying, or red bars shrinking, and blue bars growing. In week 2, Mimic was annoying fewer participants. And by week 3, a clear majority were disagreeing that Mimic was annoying, indicating habituation. For distraction, we see a similar shift over time. See the paper for plots of individual participant responses and stories from participant interviews. So, would you get used to feeling very frequent tactons all day long? There's a decent chance you'd struggle in the first week, but yes, you probably would. Thank you.
And then we have to consider fashion and compliance. Aesthetics are critical for user acceptance. As you can imagine, looking at the equipment on the left, not all users would want this piece of apparel to be visible all throughout the day. This is a Pebble smartwatch worn against the leg. It's not a prison ankle bracelet. In one of our studies involving delivery of haptic signals to participants through this device, one of the people we were working with flat out stated they would not use this in the summertime. But interestingly, it wasn't because of the aesthetics, rather it was more one of potential discomfort issues. They were concerned that with the warm weather, the band would cause sweat buildup and it wouldn't be pleasant to wear for that reason. This wasn't a problem, however, during cooler weather, during the time when we conducted the experiment. Now, the image on the right shows a series of covers that we put together for participants who wanted to hide the entire apparatus, not have that ugly wristband Velcro around the ankle being seen by everybody. Conversely, some people might want their device to be even more visible. The tech geeks among us who are showing off the cool experiment that they're running. So different users will have different perspectives on what's considered aesthetic, but it's a factor to keep in mind. So, is that it? We've covered the hardware, we've covered some of the deployment considerations. Are we done? Well, not quite. It's important to consider the environmental, experimental, and perceptual effects that your participants or users will be dealing with throughout their experiments. So, in this regard, a first consideration is that of environmental confounds. There are numerous categories we need to consider here that will affect tactile perception and perception in general. One of these is temperature. The response to a particular stimulus under warm or cool conditions can be quite different. So in the everyday, in the wild environment, what's the weather like today? That can affect your experiment. Cognitive load. What are the users doing at the same time that they're conducting the experiment? Are they busy attending to some other activity that demands their mental resources, or are they relaxing? That too is something you can control in the lab, but you don't have the ability to manage that in an in-the-wild study. You have to consider noise, whether it's from background, music being played, the street sounds around them, or elements the user is generating by themselves. This is a real confound that you can't control when you're in the wild. And we also have other interventions. So the idea of a notification being delivered through a smartwatch or a phone or some alarm going off that, again, you don't have control over. And what's particularly challenging is when that device is part of the apparatus. You're using a smartphone to run the experiment, but that smartphone will perhaps vibrate because of other reasons as well. And last, we have the induced noise that may come from the motion of the user themselves. And that's something that we consider when it comes to what strength of vibration will be noticed by the user depending on how much motion their body is undergoing just before delivery of that signal. And when we're integrating multiple existing devices, remember, you might have chosen to deploy one or more actuators, but you now have to control them, often from a single device such as a smartphone. And that control of the system, that ability to drive your actuators with the patterns that you want, may be a bigger limitation than the actuators themselves. You're often going to be limited by the libraries that are available to you. For example, in fitness trackers or smartwatches, they give you a very restricted set of capabilities that you can manage in terms of how the vibration patterns are induced. We saw this problem with experiments we ran on the Pebble smartwatch, which were great low-cost devices with a built-in ERM, but their library had to be hacked by us in order to generate the patterns that we wanted for our experiment. The Baselet is almost a perfect wireless prototyping platform in terms of haptic deployment in the wild, given that it has the form factor of a smartwatch, it's a robust device with a good battery and a nice actuator, but the effects were almost crippled by the low-pass filter that we could not control in that mechanism. If we turn to devices like the smartphones, iOS Core Haptics is a great library, but it doesn't offer HTML5 support for vibration, which may be a deterrent for some developers. And Android, even if it's built on a platform with good actuators, is still relatively limited in terms of what they expose to users with regard to the vibration capabilities. Another issue is, where can you place these actuators on the body? If the user out in the wild is already wearing a watch, you can't necessarily put another watch on that same wrist. So do you have to use another wrist? And then what about the confounds of multiple vibrations that are being generated from devices that the users or participants already wear? If they've got a smartphone that's vibrating, does that mean that whatever you're adding to their vibrational ecosystem has to vibrate differently so that it can be differentiated from the patterns that are being generated from the existing devices? Remember, you're not free to do whatever you want. You have to keep in mind what the environmental context is in which your participants are operating. Now, I've mentioned a number of gotchas throughout this tutorial, but there are more that we haven't touched on yet. There are equipment failures to consider. There are flaws in the experiment design, ranging from unrealistic expectations as to what the participants are able to manage. There are incorrect assumptions of the experimenter or of the study design itself. And there are the effects of participants who may try to sabotage the equipment or try to discover how it works under the hood. Those are all issues that you can't necessarily predict when you take your devices out into the wild. So beware, just because it works in the lab doesn't mean that it's going to work the same way when you deploy it in the field. And finally, we have to consider assessment. You run your experiment, you want to then look at the analysis of what data you collect. And in doing so, you can employ many of the traditional tools that are used in other domains. For example, questionnaires, physiological sensing, looking at galvanic skin response, or blink rate, or heart rate, blood pressure. You might look at computer-generated logs, user activity. You might go through a debriefing session with your participants. And regardless of the approaches that you take there, assessment will often turn to questions of importance such as the perceived difficulty of your participants understanding the haptic signals that were delivered, the degree of discomfort or distraction that they suffered using your device, and how does that change throughout the day or the week or the month if they're using the device for a long-term experiment. What is their level of perceived fatigue, the cognitive burden in making sense of information that's being delivered to them? How does it impact their day-to-day activity? And finally, the usefulness. Does your system, does the information that's being delivered add value to their lives? And to wrap up, we should bring back the idea as to the reason that we're doing this testing in the wild is because fundamentally we need to understand users not just in artificial lab conditions, but critically also in real life situations. And this is necessary if we want to verify the functions that we're testing that are very difficult in terms of the conditions to emulate in a lab setting. The other factor we mentioned before about habituation, that's unlikely to take place in a short lab study. It's often going to take multiple days to achieve. So a long-term study where you give the device to a user and you have it run it for extended period is often the only way to discover these nuances that will not be apparent if you confine yourself only to a lab. I hope that this walkthrough of numerous issues to consider when you're designing your own experiments and deploying haptic hardware, both in the lab and in particular in the wild, and the motivations for doing so will inspire your own work, and that the gotchas that we've outlined, that we endured through numerous agonizing rounds in our own experiments, will save you from the pain of making the same mistakes. And if so, then the tutorial was, I hope, a useful viewing for you.